In this video, we focus on Lagrangian duality for integer programming. The video consists of 4 parts. We start with a motivation for general optimization problems, then we switch to the integer programming case and discuss incapacitated facility location example to illustrate the concepts. Then we'll talk about the strength of the Lagrangian dual, and we'll show that the Lagrangian relaxation is at least as strong as the LP relaxation. And finally, we'll talk about some ideas behind the algorithms that take advantage of the Lagrangian relaxation. Okay, we start by considering a pretty general situation where we are maximizing the function f of x of n variables subject to the constraints defined by this set constraint x belongs to x capital. And these are what we call the nice constraints, meaning that the problem of maximizing f of x over the set x is easy to solve, okay? And then in addition to the constraints given by the set x, we also have the complicating constraints. There are m of them, so G maps a vector in Rn into a vector in Rm. So these constraints, when added to our problem, make the problem difficult, all right? So therefore, a common sense way of dealing with this is to try to get rid of the constraints given by these inequalities here, okay? So we can do it by introducing the multipliers for the constraints and essentially moving these constraints in the objective with those multipliers that represent a certain penalty or cost. As a result, instead of f of x, we will be maximizing the following function: f of x plus, let this multiplier be u transposed, so this will be a vector of length m with non-negative entries, and we multiply this by h minus g of x subject to x is in x. So we solve this problem for every non-negative u, and let's denote the optimal objective value by z of u. Okay, so then if we denote the optimal objective value of the original problem by z star, then we have the following relation. For any u that's non-negative, we will have an upper bound on z star. So z star is going to be less than or equal to z of u. Alright, so we call this optimization problem the Lagrangian relaxation of the original problem. So let's denote it by LR and let the original problem be denoted by P. Alright, so this is the Lagrangian relaxation. So clearly it's going to be a relaxation because we have this bound on the objective, so anytime you have a feasible solution x for the original problem, h minus g of x is supposed to be greater than or equal to 0 according to the complicating constraint, and then we multiply this by non-negative multiplier u. Therefore clearly we have this bound right here, okay? So now, normally we want to obtain as tight of a bound as possible, so therefore we will want to minimize this z of u here, alright? We consider the following problem: minimize z of u subject to u is greater than or equal to 0. And if we denote the optimal objective for this problem by z hat, then clearly z star is going to be less than or equal to z hat, because here we know that z star is upper bounded by z of u for any non-negative u. Therefore, if we minimize z of u over all the non-negative u's, then we'll obtain this upper bound on z star. So we'll call this problem right here of minimizing z of u the Lagrangian dual of our problem P. So LD is the Lagrangian dual of the problem P. For the Lagrangian dual to be useful, we need to be able to obtain z of u from here, and then we need to be able to compute the optimal objective value for the Lagrangian dual efficiently. All right. So with respect to computing z of u, we assume that f of x plus u transpose times h minus g of x can be optimized efficiently over x, just like f of x was. And then we will look at the structure of the function z of u, and we'll see that this is a convex problem, and we can solve it using the subgradient methods or some other methods for non-differentiable optimization. So if we are able to solve the Lagrangian dual efficiently, then in some cases we can actually obtain the exact solution for our original problem by solving the Lagrangian dual. So let's consider a situation when, let's say, we were able to find the optimal solution u star of the Lagrangian dual. Okay, so, and of course it must be greater than or equal to 0. And then suppose that we solve the Lagrangian relaxation with this u star right here, then we'll obtain the optimal solution to the Lagrangian relaxation. You'll have z of u star, and assume that x of u star is the optimal solution. So the fact that x of u star is the optimal solution of the Lagrangian relaxation already implies that x of u star belongs to the set x capital. If, in addition to that, it satisfies the complicating constraint, meaning that g of x of u star is less than or equal to h, then x of u star will be feasible for the original problem. So now, in order to obtain the exact bound on the optimal objective value for our original problem, we need to ensure that u transpose times h minus g of x is equal to 0. All right, so, and this is the case when the complementary slackness constraints are satisfied, or complementarity constraints. If ui star multiplied by h I minus gi of x of u star is equal to 0 for every I between 1 and m, then clearly this part right here will be equal to 0, and we will have z star equal to f of x of u star equal to z hat. So in this case, because this part is 0, f of x of u star is going to be exactly equal to z hat, and we essentially reach the upper bound for our original problem P, meaning that z star is equal to f of x of u star, so x of u star is the optimal solution for P. X of u star is optimal for P. So in this case, we say that the duality gap is equal to 0, and we are able to solve the original problem by means of solving the Lagrangian dual. All right. So, but normally we expect the duality gap to be non-zero, and we just obtain an upper bound on the original problem by solving the Lagrangian dual. So next we are going to consider the Lagrangian duality in integer programming. So we'll assume that we have all the functions involved are linear here, and integrality is a part of the constraints on the variables x. So now we are dealing with the following problem. We have maximize C transpose times x, subject to ax is less than or equal to b, then cx is less than or equal to d, and we assume that the first set of constraints would be the nice constraints, and the second set of constraints given by cx less than or equal to d is the complicating set. And in addition to this, we also require that x is a positive or non-negative integer. So what we are going to do, we will dualize the complicating constraints by introducing the Lagrangian function. So L of x u in this case is going to be C transposed x plus u transposed multiplied by d minus cx. So this is the Lagrangian function, which will be the objective for our Lagrangian relaxation. So if this was our original problem P, then the Lagrangian relaxation will be given by the problem of maximizing L of xu such that ax is less than or equal to b, and then x is integer. So this will be our z of u. So we maximize with respect to x, we obtain the objective for the Lagrangian dual z of u. And then the Lagrangian dual will be given by z hat is equal to the minimum of z of u such that u is greater than or equal to 0. Alright, so then all we discussed before for a more general case applies in this situation, and in particular if we obtain an optimal solution for the Lagrangian dual, and then if it has the property that this corresponding solution to the Lagrangian relaxation will also be feasible with respect to the complicating constraints, and the complementarity is satisfied, then we can say that we are lucky and we solved our original integer program by solving the Lagrangian dual. Alright, so however, we don't really expect to have a zero duality gap, and in most cases we'll just get an upper bound on the original objective value. So now the question is, how good is this upper bound? And we'll discuss this question, but first let's consider an example of applying the Lagrangian dual to a specific integer program. So we'll look at the incapacitated facility location problem. Okay, let's recall what the incapacitated facility location problem is about. In this problem we have the set of n potential locations for facilities that must serve m different customers. Alright, so the cost of opening facility at the location j is given by fj, so you have the fixed charge once the location is open, and Cij represents the cost of satisfying the demand of customer I from the facility j. So we don't specify the demand values for the customers. What we mean by Cij being the cost of satisfying the demand of customer I is that this is the cost if you use only the facility j to satisfy all of the demand for customer I. Okay, so then to formulate the problem of minimizing the total cost, we introduce the following variables. So we have xij is the real variable that represents the fraction of the demand of the customer I that is satisfied by the facility j. So, and then the binary variables yj's indicate if the location j is open and serves the customers. So then the overall cost consists of two parts. The first part is the cost of satisfying the demand. Okay, we look at the summation of all Cij's, Xij's for this part, and then this is the fixed charge cost of opening the facilities at the different locations. Okay, so now next we have the demand constraint, and this just tells us that the demands of all the customers must be satisfied, so the summation of Xij's over j is equal to 1. And then these constraints indicate that we can only use the facility j to satisfy i's demand if the facility j is open. Okay, so then we have the non-negativity for the real variables, and yj's are the binary variables, as we said. So now if you look at the structure of this problem, then we can see that if we remove the demand constraints, then the problem essentially becomes trivial, because each constraint will only have two variables, xij and yj, and we can easily solve the problem. Alright, so this is what we're going to do. So we'll dualize the demand constraints, we'll introduce the dual variables, and because we have the equality constraint in this case, the dual variable corresponding to the equality constraint will be unrestricted in sign, okay, and we are dealing with a minimization problem here. Alright, let's see what we get in this case. Let's write down the Lagrangian for this problem. So we'll have L of xu is equal to, we introduce the dual variables ui for each I in M, and we'll have the original objective, which is given by the summation over M and j's over n of Cij's, Xij's, plus the summation of fj's, yj's over j in n, and then we have plus summation of ui's multiplied by 1 minus the summation of xij's. So here we have the summation over n, and i's belong to M, and this is our Lagrangian function. Alright, so rearranging the terms, we can see that the coefficient for xij is going to be Cij minus ui. Alright, so let's simplify this expression to the summation of Cij's minus ui's multiplied by xij's, then plus we have the summation of fj's, yj's, and plus the summation of ui's over M. So the Lagrangian relaxation problem is given by the following. So we minimize this objective right here, subject to the remaining constraints, which are xij minus yj is less than or equal to 0 for I in M and j in n. And we have xij is greater than or equal to 0, yj is in 0, 1. Alright, so this problem is pretty easy to solve, so we can obtain z of u by just inspecting this problem and considering the possibilities for yj. First, observe that we can split this problem into n smaller subproblems, each subproblem corresponding to one of the indices j for j between 1 and n. So in particular, if we write down the part corresponding to the index j, then we'll obtain the following problem. Minimize the summation for I in M of Cij's minus Ui's multiplied by Xij plus Fj Yj, and then let's ignore the summation of Ui's for now, but let's denote the minimum of this problem by Zj of U, and the constraints will be Xij minus Yj is less than or equal to 0 for I in M, and Yj is a binary variable, and Xij's are greater than or equal to 0 for I in M. Okay, so we solve this problem for every index j between 1 and n, and then we can clearly see that z of u, the optimal objective value of this problem right here, is going to consist of the sum of zj's of u for j in n and the summation of ui's. So we ignored them before, but now we need to bring them back to obtain z of u. Alright, so this means that instead of solving this larger problem, we can now solve n simpler problems that depend on only one of the yj's and only on xij's corresponding to this index j. So we have the total of m plus 1 variables here, and we can see that this problem can be easily solved by inspection. So if yj is equal to 0, then in this case we can clearly see that all xij's corresponding to this index j must also be equal to 0, and the objective zj of u is going to be 0. And the second possibility is when yj is equal to 1. If yj is equal to 1, then let's see what we get for zj. So zj of u in this case is going to be, here we have fj coming from the fact that yj is equal to 1, and xij, the only constraint on xij is that it is less than or equal to 1 now, and clearly we need to only have xij equal to 1 when cij minus ui is negative. So otherwise we should set xij to 0. So therefore zj of u is going to be equal to the summation of the minima of cij minus ui and 0, and the summation here should be over all the i's in M, and plus fj. Alright, so we have again these two possibilities. So this is what we have when yj is equal to 0, and this is what we have when yj is equal to 1. And then clearly, to find the optimal solution to this subproblem, we need to pick the minimum of these two. So therefore this means that zj of u is going to be the minimum of the two, so which is what, 0, and the second option would be the summation of the minima of cij minus ui 0, and then plus fj, and this gives us the value for Zj of u. So we solve this subproblem for every j, and then we'll obtain Z of u from this expression right here. Okay, we obtained this expression for the Lagrangian dual objective of the incapacitated facility location problem. Let's illustrate it using a numerical example. Consider n equal to 4, m equal to 6. So we have 4 facilities and 6 customers, and the matrix C ofCij's is given by assume that the fixed costs are given by the following values. So let's evaluate Z of u, where u is given by the following vector. Alright, so we start by computingCij's minus ui's.
So we subtract 6 from the first row of our matrix, and we'll obtain minus 3, minus 1, 1, minus 4. We subtract 7 from the second row, we'll have minus 3, 1, minus 4, minus 6. We subtract 9 from the third row, minus 4, minus 3, minus 5, minus 6. 5 from the fourth row will give us 5, 1, negative 2, and 3. And then we subtract 8 from the fifth row, 3, 1, 4, 0. And finally 4 from the last row, 1, 3, 2, and 5.
Now we are ready to compute Zj's of u. Okay, so for Z1 of u, we have the minimum of 0 and the summation of the negative entries in the first column plus f1, which is 10. So this is what we have, the minimum of 0, and then summation of the negative entries gives us negative 10, plus 10 is 0, and the minimum is 0. Alright, so now for Z2 of u, we have again the minimum of 0, and then summation of the negative entries in the second column plus f2, which is 15. We have a negative 4 plus 15 is 11, and clearly the minimum is 0. Z3 of u is the minimum of 0, and now we are summing up the negative entries in the third column. So negative 11 plus 12 is 1, and once again the minimum is 0. And for Z4 of u, we have the minimum of 0, and summing up the negative entries in the fourth column, we obtain negative 16 plus 14 gives us negative 2. So Z4 is negative 2. Alright, so now we are ready to compute Z of u. Z of u is just the summation of Zj's of u plus the summation of all ui's. Therefore, we have Z of u is given by the summation of Zj's is negative 2, and the summation of ui's will give us 39. So we obtain 37, and this is the value of the Lagrangian dual objective at this point u right here. And in our case, we are talking about a minimization problem, so this will give us the lower bound on the optimal objective value. So we know that the optimal cost will be at least 37 and perhaps greater than that. Alright, next we are going to investigate the strength of the Lagrangian dual for an integer program. We are going back to our integer program with two sets of constraints. Remember, these were the easy constraints, these were the complicating constraints, and we have the variables x that are non-negative integers. So we are looking at this problem P. The Lagrangian for this problem is given by dualizing these complicating constraints and introducing the dual variables u. The Lagrangian relaxation is given by the maximum of the Lagrangian over the easy constraints and the integrality. Okay, so and then the Lagrangian dual is minimize z of u over u being non-negative. So let's look at the Lagrangian dual in detail and see what form it has. So we are going to spell out the expression for z of u. It's a maximum of the Lagrangian, and before we do that, let's assume for simplicity that the set x given by these constraints contains a finite number of points. So essentially you have a bounded set and there is a finite number of integers within the set. So this assumption is made for simplicity, and we'll derive what we want to derive regarding the strength of the Lagrangian dual for this case, but the result holds in general. Alright, so assume that x consists of the points x1 through xt, let's say, t capital. So we have t capital points within the set x. So then we can write down the Lagrangian dual as follows. So it's going to be the minimum over u greater than or equal to 0. And instead of z of u, we are going to write the maximum of the Lagrangian. And the Lagrangian is given by c transposed x plus u transposed d minus cx over x in x, meaning that x is in the set x1 through xt. So essentially this function z of u that we are minimizing is given by the maximum over x in x1 through xt of a finite set of linear functions given by c transposed x plus u transposed times d minus cx. So clearly these are all linear functions of u, so when I plug in x equal to xi for any of these points here that belong to x capital, then we'll obtain a linear function, and essentially z of u is a pointwise maximum of a set of t capital linear functions. Alright, so if you want to plot this function z of u, it will look as follows. So you have u here, z of u here, and you have a pointwise maximum of a finite set of linear functions. So this is essentially a piecewise linear convex function. Alright, so and this is what we want to minimize in our Lagrangian dual. Okay, so when we are trying to minimize a piecewise linear convex function, we can reduce this problem to a linear program, and this is what we are going to do. Actually, to avoid the confusion with the transpose, let's use k capital instead of t capital here. So assume that we have k capital points in our domain x. Alright. So now let's look at the LP reformulation of our problem. So for this purpose, let's denote z of u by a new variable eta. Okay, so then we can write down the equivalent problem to what we have here. Z hat is gonna be equal to the minimum of eta, where eta is going to be the maximum of a set of linear functions. All right, so this means that eta must be the upper bound for each of these linear functions, and we'll write down all of these constraints explicitly. So we'll say eta is greater than or equal to C transposed X. Let's use the index I here, plus U transposed times D minus CXI, where I is between 1 and K capital. And we also have the non-negativity constraints for U. Okay, so we obtained a linear programming reformulation for our Lagrangian dual, and the number of constraints here depends on the number of integer points we have in our set X. Okay, so let's see what happens when we take the dual of this problem. So let's first rewrite this LP in the canonical form by moving all the variables to the left side. So you have z hat is given by the minimum of eta, subject to we have eta minus d minus cxi transpose times u is greater than or equal to C transpose times xi, and then u is greater than or equal to 0, and the variable eta is unrestricted in sign, so the corresponding dual constraint will be the equality constraint, whereas the rest of the dual constraints will be less than or equal to constraints because u are non-negative variables. All right. So let's introduce the dual variables, denote by mu I, the dual variable corresponding to the ith constraint here. So, and I will go between 1 and k. Then we can write down the dual immediately. So, because of the strong duality for LP, we'll have z hat is equal to the maximum of the right hand side times mu I, so the summation of all of this for I between 1 and k of C transpose times xi multiplied by mu I. And then the constraints will be, so the constraint for eta column will be the equality constraint because eta is unrestricted in sign, and the coefficient for eta in each of the constraints of this primal problem is 1, so therefore we'll have the summation of mu i's for I between 1 and k is equal to 1, which is the coefficient for eta in the objective, and for the remaining constraints they will correspond to the non-negative primal variable u's here, and the coefficients are given by negative d minus cxi. Alright, so and all of this will be multiplied by mu i's, and we will have the less than or equal to constraints. So we'll have the summation of cxi's minus d multiplied by mu I is less than or equal to 0. And this is for I between 1 and k. And also because we have greater than or equal to constraints in our primal problem, all mu i's must be non-negative. So mu i's are non-negative for I between 1 and k. Now let's look at this constraint right here closely. So we have the summation of Cxi's minus d multiplied by mu I. This is going to be equal to C multiplied by the summation of Xi's mu I's for I between 1 and k, and then minus d multiplied by the summation of mu I's for I between 1 and k. But the summation of mu I's is actually 1, and the summation of mu I's Xi's, because mu I's are also non-negative, gives you a convex combination of Xi's. Alright, so therefore, by looking at all possible mu I's that add up to 1 and are all non-negative, we will obtain essentially all possible convex combinations of the points Xi's, which means that we are going to get the convex hull of this set X. Alright, so you have here C multiplied by the summation for I between 1 and k of Xi's mu I's minus d, and this is less than or equal to 0. And let's denote the summation of Xi's mu I's by X. Then we can reformulate our problem as z hat is equal to the maximum of C transposed X subject to. Now the remaining constraints with this notation essentially tell us that X belongs to the convex hull of X capital, and this constraint is going to give us Cx is less than or equal to d. Alright, so you have Cx is less than or equal to d, and then X belongs to the convex hull of X capital. Let's illustrate the result that we just established geometrically. So consider the following problem. Here the yellow region represents the set of points satisfying the easy constraints Ax is less than or equal to b. Alright, and then all the integer points within this set give the set X capital. Okay, so then the green region is the convex hull of X capital. Alright, so assume that all the points within this triangle would be the set of points that satisfy the complicating constraints Cx less than or equal to d. So then the feasible points to our problem would be the integer points on the intersection of the convex hull of X and this triangular set. Alright, so now if this is the level set for the objective, our isoprofit line, then when we solve the linear program in relaxation, we are going to get the point on the intersection of the boundary of the yellow region and our triangle. So this is the optimal solution to the LP relaxation, and the result that we have just proved tells us that the optimal solution to the Lagrangian dual will be given by the point on the intersection of the convex hull of X and this triangular set describing the constraint Cx is less than or equal to d. So essentially it's gonna be this corner right here, and we can see that our bound obtained from the Lagrangian relaxation is tighter than the LP relaxation. And in fact this result shows that the Lagrangian relaxation is always at least as good as the LP relaxation. However, if the formulation for our IP is such that essentially the set of points satisfying Ax is less than or equal to b coincides with the convex hull of X, then in this case, of course, this would mean that the yellow region essentially coincides with green, and the LP relaxation would give us exactly the same bound as the Lagrangian relaxation. But generally, the Lagrangian dual bound is at least as good as the LP relaxation bound. Moreover, for some important combinatorial optimization problems, such as the maximum click problem and the max cut problem, the Lagrangian dual has been shown to be as tight as semi-definite relaxation bounds. And these are typically much better in quality than the LP bounds. In the last part of the video, we'll talk about how the Lagrangian relaxation and Lagrangian duality ideas can be used within algorithms for solving structured integer programs. And we'll illustrate the ideas using the maximum weight set packing problem example. So let's recall what this problem is about. As we discussed before, it can be stated in form of hypergraphs, and this way it is easy to illustrate. So recall that in a hypergraph we have the hyperedges consisting of multiple vertices, not just two as in a normal graph. So for example, in this illustration here, we have a hyperedge 1, 2, 4, 1, 4, 5, and so on. And in the maximum weight set packing problem, we are looking for a maximum weight subset of vertices such that no two vertices belong to the same hyperedge. And previously we developed an integer programming formulation for this problem, so you want to maximize the sum of wj's xj's over j in V, such that for every hyperedge hi, the summation of the corresponding variables is at most 1, and obviously this inequality expresses the fact that you cannot pick more than one vertex from the same hyperedge. Alright, so let's write down the Lagrangian relaxation and see how we can utilize it. So this is a maximization problem, and the Lagrangian relaxation will look like this. You want to maximize the summation of wj's xj's over j in V, and then plus we dualize all the set packing constraints. So we'll introduce the dual variable ui that will correspond to the hyperedge hi, and we'll have the summation of ui's multiplied by 1 minus the summation of xj's for each hyperedge. And this is for all i's between 1 and m. So yeah, we have m hyperedges. The maximization is over all the binary vectors. So rearranging the terms, we obtain the following problem for the Lagrangian relaxation. So we maximize the summation over j's in V, and the coefficient for xj is wj from here, and then we'll have ui, the summation of ui's over all the hyperedges that contain the vertex j. So, and this will be the coefficient for xj. So we'll have wj minus the summation over I such that the hyperedge hi contains the vertex j of ui's times xj plus the summation of ui's over all i's. Okay, so this problem is trivial to solve because we are maximizing, and the only constraints is that xj's are all binary. We will set xj to 1 whenever the coefficient for xj is positive, and to 0 otherwise. Alright, so and this will give us the Lagrangian dual objective that we denoted by z of u before. Okay, so but what we're gonna do next, we will take the Lagrangian relaxation here, and we will look at what we get for the Lagrangian dual objective for particular values of u. So here is our z of u. We'll analyze z of u for our example. So here is the list of hyperedges that we had. There were 5 hyperedges. And then we had the intersection graph representation for our problem. And recall that our set packing problem in the original hypergraph is equivalent to the maximum weight independent set problem in this intersection graph here. But anyway, we have 5 hyperedges, and we'll consider the vector u given by the following values. So you have 3, 3, 1, 2, 0 are the values of the dual variable ui corresponding to each hyperedge here. So let's consider each j in this sum separately, and let's compute the coefficient for xj in that sum. So we'll create a table here. So there are the total of 6 variables. J will go from 1 to 6. Then here we'll have wj minus the summation of ui's, essentially the coefficient that we have here for xj. Alright, so looking at j equal to 1, wj would be the weight of vertex j. So the weight of vertex 1 is 7, and then we subtract the summation of ui's over all the i's such that the hyperedge hi contains vertex 1. So the first and the second hyperedges contain 1, so it's gonna be minus 3 plus 3. So we have 1. Now for the second vertex, we have the weight of this vertex given by 5, and then minus the summation of ui's contained in the vertex 2. So it's gonna be 3 from the first hyperedge, then 1 from the second hyperedge, and 2 from the fourth hyperedge. So we obtain negative 1. For the third vertex, the weight of the vertex is 2, and the summation of ui's is going to be equal to 1, and this is the only hyperedge that contains the vertex 3. So we have 1 for the coefficient for x3. Now x4, the fourth vertex has the weight of 6, and then we subtract the summation of ui's. The fourth vertex is included in the first, in the second, and in the third hyperedge. So it's going to be 3 plus 3 plus 1. We have negative 1. For vertex 5, the weight is 2, and the summation of ui's is 3 from hyperedge 2 and 0 from hyperedge 5. So we obtain negative 1. Finally, for j equal to 6, the weight of the vertex is 3, and the vertex 6 is included in hyperedges 4 and 5, and the corresponding ui sum up to 2. So the weight is 1. So z of u for our u is going to be given by the maximum over x in 0, 1 to the power v of the following sum. We have x1 minus x2 plus x3 minus x4 minus x5 and plus x6. And then we have the summation of ui's, and the summation of all the ui's is gonna give us 3 plus 3 plus 1 plus 2 is 9. So clearly the maximum of this is going to be obtained by setting x1, x3 and x6 to 1 and x2, x4, x5 to 0. And we will obtain the value of 12 by setting x1, x3, and x6 to 1, and x2 equal to x4 equal to x5 equals 0. So this is our upper bound obtained using the Lagrangian relaxation. So, but then if we look at the solution that we obtained by setting x1, x3, and x6 to 1, it actually is feasible for our problem. So we have an independent set here, all right, so, or a set packing for our original problem, and the weight of this set packing is given by 3 plus 7 plus 2, which is exactly 12, so we achieved the upper bound, and we can conclude that we obtained the optimal solution for our problem. All right. So in this case, we were able to obtain the optimal solution to our problem by just looking at the Lagrangian dual at a particular point. But in general, you don't really expect to achieve the upper bound with the solution provided by the Lagrangian relaxation. And in fact, you don't even expect to get a feasible solution from the original problem based on your Lagrangian relaxation. So let's consider the same example, but with a different vector u. And let's see what is happening in that case. Alright, consider this vector u, for example. So now we have 1, 3, 2, 3, 0 are the new values. They still add up to 9. But they're different compared to the previous example. So if we compute again all the coefficients for xj's, then we'll obtain the following problem for z of u. So now we have 3x1 plus 2x2 plus 0x3, 0x4 minus x5 plus 0x6. So we can see that there are 3 variables that have 0 coefficients, and what remains is really the maximum of 3x1 plus 2x2 minus x5 plus 9 for x in 0, 1. And obviously the maximum will be achieved by setting x1 and x2 to 1 and x5 to 0. And that this maximum is going to be 14. So now, if we look at the solution that we obtained here, x1 equal to 1 and x2 equal to 1, clearly it's not feasible for our problem because they're a part of the same hyperedge. Therefore, we would have to clean up this solution to make it feasible first. And we can develop a heuristic based on this Lagrangian solution. So for example, we could have a greedy heuristic where we would recursively drop a vertex that has the highest value of the total weight of neighbors minus its own weight. So if we apply this heuristic to our case, then the solution that we obtain will be just vertex 1. But then we could apply some local search heuristic to improve on that solution. So let's say in our case, if we add the vertex 6 with the weight of 3, we'll obtain a larger weight independent set. And then we can also include the vertex 3 of weight 2, and we'll obtain this heuristic solution of weight 12. Well, we already know that it's optimal, right? So, but this is what an easy heuristic would give us in this case. So essentially, we have a heuristic solution given by the set 1, 3, 6 of weight 12. So now z of u for any non-negative u gives us an upper bound on the optimal objective of our problem. So we know that the solution is somewhere between 12 and 14. So how do we close this gap between the bound and the current heuristic solution? Let's look at the Lagrangian dual here, and let's try to analyze what can happen with our variables. Okay, so anytime I get a feasible solution for my original problem, it's supposed to give me an upper bound on my objective, right? So by plugging in any feasible solution into this expression here, I'm supposed to get an upper bound on my objective. So now assume that we have a feasible solution of value better than 12, so let's say 13 or higher. Okay, so and now let's try to see if x1 can be equal to 0 in such a solution. So if I set x1 equal to 0, then the highest I can have for my Lagrangian dual here will be 2 plus 9, which is 11. And we already know that my heuristic solution gives 12, so there is no way my upper bound can be 11, right? So this tells me that x1 has to be equal to 1 in any solution of weight greater than 12. And I can actually fix my x1 and say that it has to belong to any optimal solution now, right? So because it belongs to the solution of weight 12, and from the fact that if I set x1 to 0, then the highest I can get for my upper bound would be 11, and it would give me a contradiction with the fact that I already have a solution of value 12. This implies that x1 must belong to any optimal solution. So I can fix x1 to 1, and once I fix x1 to 1, this eliminates the vertices 2, 5, and 4, and the only remaining candidates are 6 and 3, and clearly now this solution that I obtain is the optimal solution. Alright? I could have analyzed other variables as well. So let's say instead of looking at x1, I could have checked what happens if I set x2 to 0. So if I set x2 to 0, then what happens? The highest I would be able to have for my Lagrangian dual would be 3 plus 9, which is 12. All right. And this means that a solution where x2 equals to 0 cannot have a value greater than 12. Alright, so meaning that if there was a solution better than 12, then this solution would have to include x2 with the value of 1. Alright, so then, if I was searching for the solution of weight greater than 12, then I would have to put the vertex 2 in that solution, and once I put the vertex 2 in, this would eliminate 6, 1, 3, and 4 from the solution that I'm constructing, and would leave only vertices 2 and 5 that are independent. So, and the weight of that solution would be 5 plus 2, which is 7, and I would get the contradiction with the fact that I'm searching for the solutions of weight greater than 12. Okay, so this would essentially prove that the current heuristic solution that I got is optimal, because if it was not, then any better solution would have to include the vertex 2, and it's clear that the vertex 2 cannot belong to a solution of weight higher than 7. So this way we can actually use the Lagrangian relaxation in a very nice and straightforward way to fix the values of the variables for the optimal solution and to prune our search tree just like we illustrated.